Alright, so now we look at section 4.7, which deals with row space, column space, and null space. Right, so recall that for an m by n matrix, A, given with those entries, the following vectors denote the row vectors, right? So it's the rows, the vector formed by taking the rows. These are vectors in Rn, okay, because they're n components, and it's an Rn because the entries of the matrix A are all real numbers. Right, so those are the row vectors of A. And again, the column vectors are just the vectors formed by taking the columns of the matrix A. Okay, now these column vectors, there are n such columns, and each column vector is an Rm because there are m rows. All right. And as I said previously, we call these column vectors. All right, now just to formalize the following, if A is an m by n matrix, then the subspace in Rn that is spanned by the row vectors of the matrix A, so you take the matrix A and you take these row vectors, right? Now the space spanned by those row vectors, in other words, what's the space spanned by those row vectors? It's a space where each vector is a linear combination of those row vectors. Okay, and we call that the row space of the matrix A. And in the subspace Rm, the space spanned by the column vectors of A, that's called the column space of A. So going back again, if you look at these column vectors, C1, C2 up until Cn, and you look at all possible linear combinations of these column vectors, then that space, you're looking at the set that contains all the possible linear combinations of those column vectors. That is the space spanned by those column vectors, and we call that the column space of A. Then lastly, the solution space of the homogeneous system of equations derived from the matrix A, which happens to be a subspace. Remember, we established that it's a subspace because if you take any two solutions to the homogeneous linear system, then if you sum the two together and you look at that, that is obviously going to be a x bar plus a y bar, and that's just going to be the zero vector. And also for any scalar multiple of a solution, there's also going to be a solution to the homogeneous linear system. Right, so that is according to our vector algebra, and that is just the zero vector. So the null space is always a subspace, and it's a subspace of Rn, right, because there are n columns, and therefore it's an Rn, and therefore that is called the null space of A. So the null space of A is just all the set or the space formed by all the possible solutions to that homogeneous linear system. Alright, so let's do our first example. They ask us to distinguish between the row space, column space, and null space. So there we're given a matrix and we are asked to find the row space, the column space, and the null space. So what is the row space? Alright, so there we've got our first row. Alright, oh my God, yes. Right, there we've got our second row. Right, so what is the row space? The row space is the span of the two row vectors. There's my first row vector. Right, there's my second row vector. Okay, so that is my row space. What is my column space? Right, so get the column vectors there. There are my column vectors, C1, C2, and C3. Okay, now the column space then becomes, we'll denote the column space by C. It is the span of the column vectors. Right, so there's my first column vector, second column vector, right, third column vector. Right, so that's my column space and my row space respectively. So what is the null space? Right, so we need to find the solution to that linear system. Okay, so we take the matrix A, and we've got our variables. It's a 3x1 matrix. Right, so there's our 0 matrix. Right, and from there we've got, and there we're given our two equations. Right, using parameterization, we can set z as a fixed real number. Then we can solve for y and z as minus t. And so the null space becomes, okay, so the null space is all vectors of that form there. Right, so we'll call it the null space. N is the set of the solution space. So it's all vectors of that form where t is a real number. Alright, so that is the null space. Alright, so next we have, recall that if we take the matrix A and we multiply it with a column vector, and we go and multiply this row with that column, this row with that column there, carry that process through and multiply that row with that column there, and that can be expressed as this linear combination, that linear combination, where in fact we have the column vectors of A, and we're writing a linear combination of the column vectors of A down. So it turns out that A times X, where X is a column vector, can be represented as a linear combination of the column vectors of the matrix A. Now that's easy to verify that. It's just applying the normal product, matrix products operations. That brings us to this theorem here, which is a direct consequence of this observation. If you have a system of linear equations that correspond to that system Ax equals b, then we say that is consistent if and only if the vector b is in fact in the column space of A. Right. So if we take that b, that column vector, we want b to be equal to Ax. In other words, essentially what we want is we want this vector b, which is that column vector, we want that to be equal to that. In other words, it's the same as saying that b is in the column space of A. B is in the column space of A because we need to be able to write b as a linear combination of the column vectors of A. And that's the same as saying we can find an x1, x2 up until xn such that b is a linear combination of the column vectors of A. So that's all equivalent. It's basically equivalent to saying that if this is consistent only if and only if b can be expressed as a linear combination of the column vectors of A. In other words, that's the same as saying that I can find values for x1, x2 up until xn, and that's the same as saying that AX equals B is consistent. Right, so the next example is here they ask us to show that A and the vector B given. We are asked to show that B is in the column space of A, and we are asked to write B as a linear combination of the columns of A. So all they're actually asking us is when we need to look at the solution of A, the system AX equals B. All right, so AX equals B translates into, right, so that becomes my linear system I need to solve, and that can easily be done. That we get a system of three equations. Okay, from that we can solve our linear system as, right, so we can solve for x is minus 1, z is 2, and y is minus 3. Right, so there's my first column vector. Right, there's my second column vector. Right, there's my third column vector. And there we've got our values, minus 1. Right, so there we've got our second value, minus 3. And our third value, 2. And we get our linear combination. So we've just shown that the vector 1, minus 1, 0 is a linear combination of the column vectors of my matrix A, and we've expressed it as a linear combination. Right, that brings us to theorem 2, or theorem 4.7.3. Elementary row operations do not change the null space of a matrix. Right, so if you have linear systems, you get a linear system from your from this equation here, and you have set up a linear system. That's a homogeneous linear system. And if you apply row operations to A, it is most certainly not going to influence the answers that you get to, because essentially to get to the answers you have to reduce A into its reduced row echelon form, and the null, that's not going to change the null space. Right, the second one, elementary row operations do not change the row space of a matrix either. Right, so let's see why that is the case. I'm not going to write out a proof, but I'm just going to illustrate it with an example. Right, so let us take that matrix, m by n matrix, and let's look at the row space. The row space is just a linear combination of the row vectors of A. Let's take a vector v and write it as a linear combination of the row vectors, and R1 denotes the first row, R2 denotes the second row, up until the mth row. Okay. There's a linear combination between of the row vectors of A, and V is obviously in the row space of A. Now let's take, for argument's sake, let's do one row reduction on A. Let's take 3 times the second row plus the first row. So I'm going to change the first row by taking 3 times the second row and adding it to the first row. So there's my operation. Alright, now doing that, that's going to give me a new matrix. It's going to give me a new matrix that's going to have a different first row. Right, so let's call this new matrix A prime, and you can see the A prime has got a new, it's got a new first row, and the new first row is that row there. Okay, all the other rows still stay the same. Let's go back to the vector v. So we can take the first row of A, we can add 3 times the second row, and we can subtract 3 times the second row. So I've not really essentially done anything, and that becomes then. All right, then just regrouping the term, you can see that term becomes the new row R1 prime, and we keep the R2 and all the other rows the same. So this is going to be a new coefficient. Right. Now, we go back to this matrix here, A prime, right? And we go back to the vector V. We said the vector V is that linear combination, right? So what does this mean? It means that the vector V bar is still in the row space of the new matrix A prime, because it's a linear combination of the row vectors. Now, I've only done one operation. You can do any number of row reductions that you want. The vector that you choose originally that's in the row space of my original matrix A, that vector is not going to change. It's going to be in the row space of any number of row reductions. Right, so the matrix that you form by repeatedly reducing A, the vector V is going to be in the row space of that reduced matrix as well, in the rows of that reduced matrix. All right, so that brings us to theorem 4, which says that if A and B are row equivalent matrices, then number 1, a given set of columns of A is linearly independent if and only if the corresponding columns of the matrix B are linearly independent, right? And given a set of column vectors of A, if the given column vectors of A forms a basis of the column space of A, that happens if and only if the corresponding column vectors of B form a basis for the column space of B. Right, so I want to just look again at the first point. Why is it that if you have a linear independent columns in A, why is it then that those same corresponding columns in B will also be linearly independent and vice versa? Well, it's a very similar argument to the one I used to explain theorem 3. Right, so let's take my matrix A again. And again, we're not proving the theorem, we're just using an example to illustrate it. Right, so let's say my first two columns are linearly independent. So let's take first column, and there's my second column vector formed by my second column. So we assume that these two column vectors are linearly independent. So write that formula down. We know that the only solutions to the k's is the trivial solution. That is where k1 is equal to k2 is equal to 0. All right, let's go back to the previous example. So let's just use one row reduction. We change the first row by adding 3 times the second row to it to form a new matrix. It's going to have a different first row than A does. And let's call this matrix A prime. Okay, so there's my matrix A prime. And it differs only in the first row because that's the row reduction I did to change it. Okay, so that is my, we take that separately, and what we want to do is we want to answer the following question. Like we want to show that the first column and the second column of A prime are linearly independent. I take my first column vector. I take my second column vector there. Okay. Right, and write the 0 vector is a linear combination between those two column vectors. Let's call it C1 and C2. Okay, now we want to show that C1 must be 0 and C2 must be 0. Recall that A11 prime is the first entry, first row in the first column, plus 3 times the entry in the second row in the first column. And A12 prime is the is the entry in the first row in the second column plus 3 times the entry in the second row and the second column. Right, so take it separately and replace the first row of each of the column vectors. All right, so from this equation we have that C1 times that plus C2 times that is equal to 0. Right. Okay, so then we can write that matrix equation. We can write it in this form here. Okay. Right, so now the question is, what happens to these terms? What happens to these terms? We know that C1A21 plus C2A22, there's C1A21 plus C2A22 is 0. So this matrix plus that matrix is going to be the 0 matrix. Alright, so the moral of the story is those yellow parts, like I said, are going to fall away. Okay, and we're going to be left with that. But this is the column, the first column of the matrix A, and that's the second column of the matrix A. And we assume that these two columns are linearly independent. So that is literally going to force C1 to be equal to C2 to be equal to 0. So what have we seen here? What is the main thing that we can get from this? Is that if you, as in this example, we assume the first two columns of the matrix A, they're linearly independent, and then we changed a row. We added 3 times the second row to the first row, and we formed a new matrix, and we showed that the first two columns of the new matrix is also going to be linearly independent, and vice versa. Right, so if you can do it for any two row equivalent matrices A and B. If you go from A to B, and A has columns that are linearly independent, then B, the corresponding columns of B is going to be linearly independent, and vice versa. If you have linearly independent columns in B, then their corresponding counterparts in the matrix A are also going to be linearly independent. Right, so the second part, if we're given a set of column vectors of the matrix A, and that set forms a basis for the column space of A, that happens if and only if the corresponding column vectors of B also forms a basis for the column space of B. Right, so you can't have one without the other. That's if A is and A and B are row equivalent. So again, I'm not going to prove this, but I'm going to just illustrate this quickly with an example. We're going to use the example we used in the illustration for Theorem 4, the first part. Alright, so there we've got our matrix A, and let's just assume for argument's sake that the first two columns of the matrix A forms a basis for the column space of A, and we call it B subscript C. The basis for the column space of A it's those two vectors. So let's assume for argument's sake, as an illustration, that the first two columns of A forms a basis for the column space. All right, and there's our matrix B. And we obtained B from A by applying this row reduction. We changed the first row by adding 3 times the second row of A to the first row of A. And that created a new matrix B, which is row equivalent to A. Now my aim is to now show that the first two columns of B forms a basis for the column space of the matrix B. Right, now we remember when we illustrated with an example the first part of Theorem 4. In other words, if you have a set of column vectors and those column vectors of A are linearly independent, then the corresponding column vectors for the matrix B are also going to be linearly independent. Now what this means is that because this is set as a basis for a column space of A, it means those two vectors, this one and that one, is going to be linearly independent. Now that is going to imply that in my matrix B, the first two column vectors are going to be linearly independent. Right, so therefore by the first part of Theorem 4, because the first two columns of the matrix A, those column vectors are linearly independent, it means the first two column vectors of B is linearly independent. So now I just need to show that this set here is a basis, so I just have to make sure the spanning property holds. Alright, so let's pick a vector V. Let's pick a vector V to be in the column space of B. In other words, it is a linear combination of the column vectors of B. Alright, and just for argument's sake, V is just, again, it's just some column vector, right? Alright, so now what I want to do is I want to go back to the matrix A. So I want to reverse this operation to go back to the column vectors of A. Alright, so I'm interested in the first row of that matrix equation. So there we take V1 is clearly equal to C1 times that, C2 times that, up until there, right? And we get it from that part there. Now, the operation I used to get the first row of the matrix B, recall that operation? Right, it was the operation, I took the first row of A, I changed it by adding 3 times the second row of A. Right, so doing the replacement, we get the new vector, well, the same vector V1, but we replaced these terms. Remember, we get A11 prime by taking 3 times the entry in the second row in the first column and adding it to that, and we get the subsequent entries as well. Right, so in my original matrix equation, I do the substitution in the first row and get the following. Right, so there we get the substitution. Alright, so again V1 is equal to this whole term, that term there, and from there we can get, right, so we get that there, okay, and plugging all that back into the matrix equation we get that new matrix equation where the quantity V prime is, where the quantity V prime is this whole quantity, right? So it's that whole quantity there. Alright, so also observe that we can do another substitution. V2 is equal to C1A21 plus C2A22 up until Cn A2n. Right, so then we get that quantity there. So you can see that corresponds to that term there, that term corresponds to that term there, up until there, that term corresponds to that term there. Alright, so from there we get that V prime is V prime is V1 minus 3V2. So we get that expression